Isomers are compounds that have the same molecular formula. There are different types of isomers. But for us, we're going to limit ourselves for the two types of isomers in there, the structural and the geometrical. We're going to define each and we're going to give examples. So both of these isomers, they have the same molecular formula in there, whether if they are geometrical or they are structural. But whenever I'm working with the structural isomers, these are isomers that have the same molecular formula, but they have different connectivity of atoms. What does that mean? It means that if I give you C2H6O, and I would ask you, go ahead and draw all the structural isomers for this formula, meaning that all the compounds that have that same number of carbons, hydrogens, and oxygens, but you're going to draw it differently every single time. So what you do is, we know that we have two carbons in there and we have an oxygen in here. So what you do for these, whenever you want to draw the structural isomer, since oxygen is in there, you have nothing around but calculating your DBE, guys, because you want to know if your structure has a double bond or a cycle in it. So you calculate your DBE is the number of carbons times 2 plus 2 minus the number of hydrogens, which is 6 divided by 2, and that is equal to 0. Okay? 6 minus 6, it's equal to 0. A dB of 0 and an oxygen in the molecular formula means two things. I have here an alcohol and I have an ether, or I have an ether in there, okay? Because the alcohol has a general formula of an ROH and the ether has the formula of an ROR. And it really helps if you go ahead and draw their general formula so that when you connect them together, you know what you're doing, okay? These two are considered to be structural isomers for this molecule here, because I can go ahead and have this R being all the carbons, so I'm just going to connect those two carbons and do an OH and put the hydrogens in there, and that will be a C2H6O. And this is a primary alcohol. Why it's a primary alcohol? Because this is the carbon alcohol part, and that one is connected to one carbon. So this one is going to be a primary alcohol. This is one type of structural isomer that carry the formula C2H6O. Another way I can draw C2H6O is by putting the oxygen in between two carbons in there. Because I have two carbons, I'm just going to separate them equally and make this a CH3, and this one is another CH3. Now this one is what? This one is an ether. So see, from that same molecular formula over here, I could get two ways of writing the molecule. This one is a Lewis structure of the C2H6O, and this one is a Lewis structure of the C2H6O in there. Both of those are Lewis structures, and both of those are different ways to write the C2H6O. So they do have different connectivity of atoms in there, but the same number of carbons, the same number of hydrogens, the same number of oxygens. We call those structural isomers. As we introduce more functional groups for every chapter in the properties of functional groups, we're going to have examples of structural isomers for aldehydes, for ketones, for amines, and so forth. Okay, but now we're going to limit, since we are explaining alkanes, we're going to limit our structural isomer examples to alkanes. So this is how you go ahead and draw the structural isomers of C6H, it's actually C6H14. And there. So for this one, in order to draw the structural isomers of any alkane, it follows the CnH2n plus 2. So I know that this guy is going to be an alkane. dB is equal to 0, so I can go ahead and proceed. It's as if it's asking me to draw different structures that have different names in there, so different types of structures, and all of them, they need to have a C6H4 molecular formula. There are a couple of steps There's no rule actually, but there are some steps that you can follow that can make the stuff easier or the method easier for you. So the first thing, as I did over here, you check what type of hydrocarbon you are working with. It's an alkane, you know that there is no double bond, you proceed. Step number 2, you draw the N chain, which is the straight chain, no branches. And here I do have 6 carbons, so go ahead and draw the skeleton for the 6 carbons. And then step number 3, we're going to take 1 carbon and move it along the chain. And every time we do this, we want to generate a new structure. If you generate the same structure, just to cross it out, okay? So here I'm just going to take 1 carbon and I'm going to move it along the chain. So I'm just going to put it on carbon number 2. And then I'm going to take that same carbon and put it on carbon number 3. So this is going to be 1, 2, and 3. Guys, you can number anywhere you want because we're not numbering here to name. Numbering has rules, but whenever you are putting the substituents or putting a group on the chain, it really doesn't matter here. You can number from the right, you can number from the left. So here the substituent is on the 3rd carbon, here the substituent is on the 2nd carbon. See the difference in there? But both, they share the same formula, which is the C6H14. If I put the CH3 here or if I put it there, it's still, if I number it from the side, it's going to be 1, 2. So these two are the same. Just represent one of them. Don't do 2 of them, okay? Now, after I take 1 carbon and move it along the chain, I cannot move it further. I did put it on carbon 2. I did put it on carbon number 3. After that, I'm going to start replicating my structures. Then now I'm going to take 2 carbons and move them along the chain. You have the possibility of putting the 2 carbons on the same carbon or putting them on adjacent carbons. That's it. So now we can go ahead and count our structure. How many did we generate? It's 1, 2, 3, 4, and 5 structural isomers of molecular formula C6H14. 5 structural isomers. But you keep moving the carbons until you get a different structure every single time. Let's have another example over here. For example, if I ask you, go ahead and draw the structural isomers for C7H16. So again, let's move by steps. Step number 1, this follows the CnH2n plus 2, which is an alkane. It's a C7H16, so that is going to be an alkane in there. And the alkane has the DBE equal to 0. Guys, it's so important to know that it is a chain. So now we can move on and we can draw the N chain first, the 7 carbons. So I'm just going to connect the 7 carbons. And notice for these types of questions, I go ahead and answer them in the skeletal forms. 1, 2, 3, 4, 5, 6, and 7. So that is going to be my first. Now I'm going to take 1 carbon and move it along the chain. Okay? Move it along the chain, but I don't want to replicate though. So I'm going to take 1 carbon. So now my chain is going to be 6 carbons. So that is going to be 3, and this is going to be 3. This is a total of 6. I'm going to take 1 carbon and move it along the chain. So now my substituent is on the 2nd carbon. I can make it on the 3rd carbon. This is 1, 2, 3, 4, 5, and 6. I can make it on the 3rd carbon over here. So I can put it like that on carbon number 3 in there. Okay, there you go. This is carbon number 2. If I go ahead and put the CH3 here, then I can start numbering from the side, and this one is going to be still on carbon number 3. So I am done from moving the CH3s in there. This is 1, 2, 3, 4. Yeah, I am done from moving the CH3. So I'm done from taking 1 carbon, moving it along the chain. Now I'm going to take 2 carbons and move them along the chain. Taking 2 carbons from C7 will end up having C5. Okay, so we're going to end up having C5. So let's draw the 5 carbons. This is 1, 2, 3, 4, and 5. I'm going to take 2 carbons and put them on 1 carbon. Your total number of carbons have to be 7 carbons. I can take 1 carbon, put it here, 1 carbon, put it there. This is going to be 1, 2, 3. Okay, so on carbon number 2 and carbon number 3, I have a branch. I can put the branches on carbons 2 and 4. That will be different. So I can put a branch here and I can put a branch there. So this is carbon number 2, 3, and 4. That is going to be different in there. And I can put both the branches on carbon number 3. And there are both CH3s on carbon number 3. 1, 2, 3, 4, 5, 6, and 7. Always count just to make sure that you have your 7 carbons in there. So far, how many I have? 1, 2, 3, 4, 5, 6, and 7. Now I can take 3 carbons and put them along the chain. If I do this, then I'm going to end up having 4 carbon chain over here. I can put 2 carbons on this carbon and I can put 1 carbon over here. Okay. Pay attention that every carbon needs to have 4 bonds and not more than that. So I can end up having this structure over here. I can move around with the carbons, but any other move that I do will create structures which are similar to these. So I'm going to stop here. The rule says that as the number of carbons increase, as the number of structural isomers increase. So we write as many or as much as we can from these structural isomers, and these are the structural isomers of C7H16. The other type of isomers is the geometrical isomers. Now, geometrical isomers is a type of isomer, so they should have the same molecular formula, but they are not structural. Pay attention. So this means that they need to have the same connectivity, not different, same. So geometrical isomers, these are isomers that have the same molecular formula, but their connectivity is the same. The difference is the rotation in space or the orientation of the atoms in space. This is the difference in it. Geometrical isomers is another term for stereoisomers since I'm working with rotation. So stereoisomers. So stereoisomers is different types, but for us, we're going to limit our stereoisomers to geometrical isomers only. So whenever you see stereoisomers, I mean by that geometrical isomers. And geometrical isomers, they have the same molecular formula, same connectivity, but different orientation of the groups in space or different rotation of the groups in space. There are 2 ways where we can draw geometrical isomers, either in a cycle or in a double bond. In both, they need to have 2 groups in there. So for the cycle, if I'm working with a cycle, I would need to have 2 substituents on that cycle. This is a cycle of 6-membered rings in there. And on that cycle, I have 2 substituents coming off the cycle. See, this is a wedge line. So these CH3s are pointing towards you in there. Okay. So when these 2 CH3s, they are on the same side, whether both they are up or both they are down. These 2 are down and these 2 are up in there. We're going to call these cis isomers. Cis means that substituents are on the same side. The substituents have to be 2 substituents and they have to be on the cycle in there. It's not necessary that they are on carbons 1 and 2. They can be on carbons 1 and 3, 1 and 4. It really doesn't matter, but they have to be 2 substituents. They cannot be 3. Okay, so please put this as a note. If I have something like this here, and if I have, let's say, a CH3 in there, a CH3 in there, okay, and then I have another CH3 like that. The moment I see 3 substituents on the cycle, I cannot term it as a cis or trans. So cis and trans, they only belong to 2 substituents on the cycle. So with this one, there is no cis or trans in there. Cis and trans exists whenever I have two substituents on the cycle. And the substituents can be anywhere on the cycle, not necessarily on carbons 1 and 2, okay? So if they are on the same side, we're going to call them cis isomers. These are cis stereoisomers or cis geometrical isomers. If they are on opposite sides, see, one of them is up, the other one is down. Here, this one is up, this one is down. So these two are on opposite sides in there. We're going to call them, these two are the same, by the way. These two are the same. And we're going to call those trans isomers. So this is the difference between cis and the trans isomers. Between the cis and the trans, you cannot do rotation. So there is no rotation from here to there unless you break the cycle. You cannot make cis substituents trans unless you break the cycle, twist it, and then connect it back. And then you go from the cis to the trans. So this is why we call those geometrical isomers. They have the same connectivity. Everything is the same. So if I am to classify or compare this structure here with this structure there, okay, and I'm asked what is the relationship between them, then I'm going to go ahead and take a look at them. See, this is connectivity 1, 2, and this is connectivity 1, 2 again. So you have a 1, 2 connectivity, a 1, 2 connectivity. This is the same connectivity, but the orientation of the groups around the cycle, they are different. These two are on the same side, which is cis. These two are on opposite sides, which is trans. So I'm going to classify both of these as a geometrical isomers. Okay, the moment you see a cycle that has more than two groups on it, you cannot classify it as cis and the trans. Pay attention to that. Let's have an example over here. So if I have something like this, again, cycles can be a cycle of 3-membered rings, a 4-membered rings. In there, let's do a 4-membered rings in there. So if I want to draw a 4-membered ring in here, and if I am showing a CH3 and a CH3 in here, and then I am showing another structure where I am having a CH3 versus a CH3 in there, and I am showing a third structure where I have a CH3 here and a CH3 there. And let's label those as A, B, and C. And the question is, what is the relationship between A and B? So whenever you have a question like this, please look at the connectivity. The connectivity is the same. Here I have it. You can number from any carbons. We can start numbering from here or numbering from the other carbon. It really doesn't matter, but put the same numbering for both. So on carbon number 1, this is carbon number 1. On carbon number 4, this is carbon number 4. So I have substituents on 1, 4, substituents on 1, 4. Same connectivity, but this one is a trans. And this one is cis. So definitely these two are geometrical isomers. Okay, so we call them geometrical isomers, or we can call them stereo isomers there. What's the relationship between B and C? Now for B and C, the connectivity is different. See, the CH3s are on carbons 1 and 2 versus 1 and 4. So these two are not geometrical isomers. These two, because the connectivity is different, we call them structural isomers. Okay, so pay attention to that. When the connectivity is the same and the orientation is different, then these are geometrical isomers. When the connectivity is different in there, I don't care about the orientation. Different connectivity, then these two are structural isomers. So B and C are structural isomers. A and C are also structural isomers in there. So the only ones that are geometrical isomers are the 1, 4, which is the cis and the trans in there. So cis and trans can exist in cycles. Another way that you can also write cis and trans is around the double bond. So two ways that cis and trans exists. They exist in cycles and they exist in alkenes. And if they exist in alkenes, the groups need to be the same. And if they are the same, if you show them on the same side, then this is going to be a cis alkene. And if you show them on opposite sides, then this is going to be a trans alkene. Both of these, if I want to classify them, these are considered to be geometrical isomers. Okay, so the orientation in space can be around a cycle, but on one condition you need to have two groups and not three in there. So around the cycle, so cycle can have two substituents on it, and they can be cis or trans. And the alkene also can have two substituents on the alkene. So what you do is you highlight your double bond in there and look at the groups that are on the double bond. If the groups are on the same side, these here are two CH3s. If they are on the same side, this is cis. If they are on opposite sides, then this is considered to be trans. Another term that we want to define is the conformation. Okay, what is conformation? Conformation is not an isomer. Okay, conformation is a simple term that we give whenever we rotate. And we rotate around the carbon single bond carbon. So conformation is simply the rotation around a carbon single bond carbon. So you don't have cis and trans in here. Okay, so let's say, for example, if I have this alkane in there, and on the alkane I do have a chlorine here, and I have a chlorine here. Of course, put all the hydrogens there. So I do have the hydrogens. I'm not drawing any tetrahedral structure here, although you can draw this chlorine to be pointing in front, but still it's not going to be cis or trans because this is not a cycle or an alkene. Okay, and I have another structure over here where the chlorine. So I have a chlorine over here, and then the hydrogens. And I would ask you, okay, what is the relationship between those? Because these two are the same because the connectivity, see, this is 1, 2 there, and that is 1, 2 there. On carbon 1, I have a chlorine and 2 hydrogens. Same thing, carbon 2, I have a chlorine and 2 hydrogens. But notice that the orientation of the chlorines are different. I cannot call them trans over here, and I cannot call these two chlorines cis, but the rotation is different. The rotation here is around the carbon single bond carbon. I don't have an alkene, I don't have a cycle. So if I go ahead and rotate, this carbon there, then this chlorine is going to be up. So these two, they differ by rotation around the carbon single bond carbon. So I call normally these two as conformers or conformations. So these two are considered to be two conformations of the same molecule in there. It's just like you are rotating it around the carbon single bond carbon, and you are viewing it differently in there based on the orientation of these two chlorines. Again, this is not cis, not a trans, because cis and trans, they exist only around the cycle or a double bond. So if you have a rotation around the carbon single bond carbon, this will be called conformation.